Attention is all you need. Part 1. Introduction. The bottleneck problem. In Part 0, the abstract promised something huge: better results, faster training, and a model built purely on attention. Part 1 is where the authors justify that promise. In the introduction, they pinpoint the bottleneck that made older models slow, and they explain why removing recurrence changes everything. By 2017, recurrent neural networks, and specifically two variants called LSTMs, long short-term memory, and GRUs, gated recurrent units, were the go-to state-of-the-art models for sequence modeling and sequence transduction, because they were better at holding on to important context over long sequences. Sequence transduction just means turning one sequence into another, like translating English into French. First, what's a neural network? Think of it as an AI system that learns patterns from examples, similar to how our brains learn from experience. Now, language comes as a sequence, word after word. So researchers needed a model that could keep track of what came earlier while reading what comes next. That's exactly what recurrent neural networks were built for. They read the sequence one step at a time, updating their internal state as they go. Researchers then scaled that idea into the encoder-decoder setup, where the encoder reads the input sequence and the decoder generates the output sequence. With LSTMs and GRUs, they kept improving these systems and pushing performance higher. But that same step-by-step design is also where the bottleneck comes from. Sequential computation. You're forced to compute the sequence step by step. Recurrent models process sequences position by position. They align each position to a specific step in computation time. At each step, the model produces a hidden state. You can think of it as the model's working memory at that moment in the sequence. This hidden state is calculated based on the previous hidden state and the current input. So you get a chain. Step 1 depends on Step 0, Step 2 depends on Step 1, and so on. Think of it like reading a sentence word by word, and at each word, you're updating your mental note about what you've read so far. But there's a catch. You can't think about word 10 until you've finished processing words 1 through 9. You can't skip ahead. You can't process multiple words at the same time. That inherently sequential structure prevents parallelization within a single training example, and that becomes critical as sequences get longer. Now, why does this matter so much? Modern GPUs, graphics processing units, the chips that train these AI models, are incredibly powerful at doing many things simultaneously. But with RNNs, you're forcing them to work on one position at a time, waiting for each previous step to complete. It's like having 1,000 workers standing idle, while one person does all the work. And it gets worse as sequences get longer. Longer sequences mean more memory for those hidden states. More memory per example means you can fit fewer examples in a batch. A group of examples processed together. Smaller batches mean you're using your GPU less efficiently, which means slower training. Researchers tried to work around this. There were factorization tricks, mathematical optimizations to reduce computation. There was also conditional computation, which means computing only what's absolutely necessary. These approaches did improve both efficiency and performance, but the fundamental constraint of sequential computation remained. You still couldn't escape processing things one step at a time. And that is where attention mechanisms enter the picture. Attention lets the model focus on the most relevant parts of the input, regardless of distance. It can model relationships between any two positions without having to pass information step by step through every intermediate token. It's like being able to instantly look back at any earlier word in a sentence, instead of relying on a long chain of memory. As we mentioned earlier in Part 0, by 2017, attention was already an integral part of the strongest sequence models, but in almost all cases, attention was still used in conjunction with a recurrent network. Attention was the helper, not the one running the show. This time, the researchers flipped the script. They proposed the transformer, a model architecture that completely abandons recurrent connections and instead builds everything around attention, with simple feed-forward layers on top, to model global dependencies between input and output. The payoff is significantly more parallelization. Because you're no longer forced to compute token positions one by one through a recurrent chain. And they report that in their fastest configuration, the model can reach a new state-of-the-art in translation quality after being trained for as little as 12 hours on 8 100 GPUs. That's the punchline of the introduction. Remove the sequential bottleneck, and you unlock speed and scale without giving up quality. So the introduction sets the stakes. The old approach wasn't failing on quality, it was hitting a scaling wall. In Part 2, we'll look at what researchers tried before the transformer: convolutions, earlier self-attention ideas, and memory networks, and why none of them fully removed the bottleneck.